All right. So how many people have taken the GREs? I was still missing Philippe and... Okay, how many taking the GREs in math? In physics? How many taking both? Okay. So I'm just changing the order of the topics just a little bit right now, just because so many people are taking the GREs. I want to cover the residue theorem. So it's kind of sad that we're not going to do motivation. Hello. Hello. Welcome to the unmotivated complex analysis. Oh, cool. Well, the motivation is basically some of you are taking the GREs, so we need to make sure we cover this material before you take the GREs.
Ah, yes, I appreciate it.
Yes.
Yeah. Also, nice setup.
Oh, thank you. Now, unfortunately, Umang probably won't be able to get either audio or video from this, but you know, he'll at least get some blurry pixels and whatnot.
I think we should let's put it on that board today.
Hi, Uma. Okay, sorry. All right. So we're skipping the motivation. We're going to go back and do the motivation later. We're going to do accumulation points later. Right now, I want to start and jump into the Cauchy residue theorem. So in terms of applications, this is the key application is calculating integrals. And in fact, converting integrals to algebra. It's a little bit more algebra than what you did in 7th or 8th grade, but it is still much better than having to do an actual integral. There's also a lot of theoretical applications, which I will not talk about today, but I will talk about later. So the first is some definitions. So the first definition is a pole. We say F has a pole of order n at z0 if I can write f of z as a negative n z minus z0 to the n plus dot 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 plus a to the minus 1 z minus z0 plus g of z, where g of z is some converging power series. Okay? So basically, it's a Taylor series that goes backwards a little bit. The important thing is, for us right now, it's only going backwards a finite amount. I'm not allowing the series to go off to negative infinity. Okay? I'm forcing myself to stop at minus n for some integer n. Okay? So now, when you look at this, which do you think matters the most in terms of trying to understand the behavior of the function? The negative nth term, the negative n minus first term, or the negative first term? Which one? The negative first. Well, why not the minus n? Because if it's blowing up, this piece is going to blow up more than anything else as z goes to z0. Doesn't it seem like this should be the most important piece? You're right, it's not. It's the least important. The negative 1 is the most important. Why is the negative 1 piece so important? Remember, when we integrated, recall the integral over some circle of z to the n dz was 2 pi I if n is minus 1 and 0 otherwise. So when I do the integrals, all that really matters is the negative 1 coefficient. The other terms don't matter for the purposes of integration. So we're going to give the negative 1 term a special name. So we call it the residue. So the residue of f at z0 is a minus 1. And anything that is this important should have multiple notations. We could write it as the residue at the point z0 of f. What's nice about this notation is it tells you, here's the point that's where the action happens, here's the function under discussion, and what am I doing? I'm taking the residue. Another notation which I'll occasionally use is a minus 1 of f. The advantage of using a minus 1 of f is this reminds you which function it's the residue of. But of course the problem with this is you don't necessarily know what point. So you might even want to write maybe a minus 1 of z0 or a minus 1 of z0 in f. Usually you don't bother to put in the function f because usually the function f is clear from context. You know, if I'm integrating a function, I normally don't change the function I'm integrating in the middle of the process. But if you have several functions that you're playing with, or if you maybe break a complicated function up into simpler functions, it's not a bad idea to do something like this to just highlight what's going on. Okay, so the old fact that we have, if we let P of z be the sum of the negative terms, negative index terms in F. So that would be this part over here. Okay? Then, if C is a sufficiently small circle about Z naught, then we have 1 over 2 pi I, the integral over C of f of z dz is the same as 1 over 2 pi I, the integral over C of P of z dz, and that's just equal to the residue at Z naught of F. And again, this is just because when we integrate, all that matters is the negative 1 term. Okay. Any questions on this so far? All right, so far basically definition, restating old result. So now the question is, why is this useful? Well, it's useful because it's going to allow us to quickly calculate some integrals. However, if we're going to quickly calculate integrals using this method, what will we need to be able to do?
Sum the index terms.
Sum the index terms, find the index terms. The great Richard Feynman has a wonderful story or anecdote about how people often write things down in such general notation that it becomes useless. And whenever you're writing things down, you want to make sure that at the end of the day, you have something that you can compute. How many of you have seen Feynman's formulation of physics in one equation? Feynman has shown that physics reduces to solving one equation. So you just have to solve u equals 0. And so u is defined as the following. So you basically take every physics law and you subtract and square. And so the only way, real numbers like this can be 0 in the sum is if each one is 0. So this is a way to encode all the equations of physics into one equation. Is this useful? No. Not useful. U does not stand for useful. Okay? It stands for unworldliness in his notation. Okay? So just because I can reduce something doesn't mean it's helpful unless I can actually compute it. So what I want to do before I talk about using this to evaluate integrals is I want to show you how to find residues. Because if I can't find residues, then the residue formula will be useless. So the key idea in finding residues is essentially to use the geometric series formula. So finding residues. So imagine I give you the function f of z is 1 over z squared plus 1. For those of you who took probability with me, this is one of my favorite functions, at least when you restrict z to be real. Okay? It's a nice function. I'll talk about why I like it so much in a little bit. Where is this function bad? Plus and minus I. Plus and minus I, right? So the poles, we need z squared plus 1 to equal 0. So z squared equals minus 1. So z is plus or minus I. And so I want to figure out what are the residues. Now for this function, I can actually see how to factor it. Z plus I and z minus I. So if I want to find the residue at I want to write things in terms of powers of z minus I. So to find residue at I, express as powers of z minus I. One of these two terms is actually pretty easy to express in terms of powers of z minus I. right? Which term is easy to express in terms of powers of z minus I?
1 over z minus I.
The 1 over z minus I, yes. Which one requires a little bit more work? The other one. So I want z minus I. I have z plus I. So let's figure out how to deal with this. I know how to deal with this. Well, z plus I, I'm going to write it as z minus I plus I plus I. I've added 0. And so again, this is a great way to find the residues, is add 0. I want a z minus I. I don't have z minus I. Let's make it a z minus I. So if I had z to the n plus I would write it as z minus I plus I to the n. Is basically we replace z with z minus I, parentheses, plus I. So now we get z plus I is 2I plus z minus I. Unfortunately for us, it's in the denominator. If it was in the numerator, we'd be done. You know, this would be my constant term. So what I want to do is I want to just go through in more depth than we need how to figure out what the residue is here. Because if I had given you a more involved problem, we'd have to do those steps. So now we have f of z is 1 over z plus I, 1 over z minus I. So we have 1 over z minus I, and now we have 1 over 2I plus z minus I. If I'm trying to calculate the residue, what is at I, what is z close to? So I'm trying to calculate the residue at I, what is z close to? I. So z minus I is really small. 2I is extremely large relative to it. I'm going to pull out the 2I. And I get 1 over z minus I, 1 over 2I, and then 1 over 1 plus z minus I over 2I. And again, if I look at this ratio, in absolute value, this ratio is going to be very small because z is close to I. How should I deal with this? Geometric series. So what would be the ratio for the geometric series? So be a little careful. Minus z minus I over 2I. Right? And so now I get 1 over z minus I, 1 over 2 to the I, and now I expand this. I get 1 minus z minus I over 2I plus z minus I over 2I squared, yada, yada, yada. And now if I just go through, I have 1 over 2I, 1 over z minus I. The next term is minus, the z minus I is canceled. I times I is -1, so the negative sign cancels, and I get a 1/4. The next term, I'm going to have plus 1 over 8I, if I've done it correctly, z minus I, like this. And so I can now calculate its residue. What is its residue?
Is that all in parentheses because of 1 over 2I in front there, or?
The 1 over 2I hits this whole thing.
Okay.
Because remember, I'm using a geometric series on this.
Right.
And I've pulled out the 2I.
Okay. And the equation down there is.
The equation down here, I've now actually multiplied this in.
Okay, got it.
If I'm calculating the residue, did I really need to calculate these other terms?
No.
No, I could have stopped. But I've got 50 minutes to fill, so I had to, somehow pad up the lecture bit. Okay. So the residue is just 1 over 2I. So we would write the residue at I of my function f is just 1 over 2I. Does that look familiar? Is there any other place on this problem where you could see 1 over 2I? Nope. function f, I claim that 1 over 2i shouldn't be surprising.
I'm sorry, can you say one more time why residues were 2i?
So all that we care about is the coefficient of the z minus I to the negative 1 piece.
Oh, right.
And that's the coefficient. I actually didn't have to do all this.
What's the difference of the denominators?
What is it is the difference of the denominators. It does have something to, it's a good thing to look at. This is a little bit of a function of the fact that it's a quadratic. But it is related to what's going on. How else could I, if I look at this function, and I'm looking at what's going on at I, this piece becomes 1 over I plus I. This is the piece I'm expanding. Well, this piece is holomorphic at I. This piece doesn't blow up when z equals I. So if I expand this, its constant term should just be its value at I. There was actually no need to do this. But again, 50 minutes, have to do something. And there will be other problems where it's not going to be as nice as this. So you want to see the method. But what's really going on here is, look, if I expand 1 over z plus I, let's call that function g of z. Then it's g of 0 plus, I don't know, g prime of 0, z minus, oh sorry, g prime of I. Because I'm expanding it at I. G prime of I, z minus I. That's what I would get if I do the series expansion. Well, gee, all I have to do is plug in I. If I instead I had 1 over z minus I to the 5th, then what term would I need from here?
1 over z minus I.
I'm sorry?
A 1 over z minus I term?
Yes. Which term would I need? If I had this to the 5th power,
That to the fourth.
I would need this to the 4th. Because to the 4th power divided by the 5th power would give me 1 over z minus I in the denominator. If I had this to the 2013th power, I would need the 2012th power here. So that's why I went through the geometric series. So if this wasn't as nice as 1 over z minus I, you'd have to do a little bit more work. But here, this is why it's going to just be 1 over 2i. And that's the faster way of getting it. So again, you can use the shortcut if you can write f of z as, say, g of z times h of z, and g is holomorphic at z naught, and h of z equals a to the minus 1 over z minus z naught. So if it looks like that, you can just use that shortcut trick to jump to the residue. And for those of you who may be doing the GREs very soon, this could be useful. I have no idea, because the GRE does not test good things. So, any questions on calculating residues?
So here specifically we were looking at the residue at I.
Correct.
Okay.
And where else could I ask for the residue?
Negative I?
Negative I. And so then this piece would be fine at negative I, and I would have to write this as z plus I minus I.
Got it.
Or I could just jump and say it would be 1 over negative 2i.
Wait, what would be the difference if you had minus I?
Well, if I had minus I, then this piece is now the piece that's good, and the 1 over z minus I is the piece I have to change. Right? And so it's essentially the same calculation. And so instead of writing z as z minus I plus I would write z as z plus I minus I. This piece would be fine, because it already looks like 1 over z minus minus I. This piece would be the piece that would be bad, and I'd have to fix. Okay. So it's now time for one of the gems of complex analysis. And so the book breaks the residue theorem into 2 stages. It first goes on what happens if you have just one point that the function blows up at, and then several points. So, the residue theorem. And then the big question is always going to be, what's the most general region where this is true? So all of our toy contours work. So omega is nice. F is holomorphic on omega, save a pole at z naught. Then the integral of 1 over 2 pi I over some curve, a little bit more generous, some curve gamma of f of z dz is just the residue at z naught of f, where gamma is a nice curve in omega. So give me an example of a really nice choice for omega and a really nice choice of a curve. Think omega is what?
Yes.
Disk. So omega is an open disk, and gamma is,
Was this in that open disk?
yeah, perimeter of a circle is the circle. Yeah. That's the case you should be thinking of. And basically, essentially, as long as we can use Cauchy's theorems, as long as we have a nice region, we're fine. All of our contours are fine. When we have this notion of path connectedness, I have a way to get from one part of the region to another without any danger. I can define a primitive uniquely. It all comes down to the need to define a primitive uniquely. And in this chapter, we'll actually see situations where you cannot define a primitive uniquely. And so the proof is basically Cauchy. So imagine, not even close to scale, but here's my point z naught, here's the origin, here's my circle. I take this to be my contour, and my function is holomorphic along this contour, and so the integral is going to be 0. I then take the limit as delta as the thickness goes to 0. I then take the limit as epsilon goes to 0. And what I get is the integral over the circle of f is equal to the integral, and we'll call this circle maybe c sub epsilon, is equal to the integral over c sub epsilon of f. And the reason this is the case is, remember, we're traveling the circle like this, so when we come down and do the small circle, we're doing the small circle in the wrong orientation. So what we get is the integral over this circle taken the right way, plus the integral over this circle taken the wrong way equals 0. So the integral over the big circle equals the integral over the little circle, now oriented correctly. Okay. And so now we just basically use Cauchy's theorem. And so when we try to see what's going on here, we have a finite Taylor series expansion that goes backwards at most a finite number of places. And the only one that really matters is the 1 over z minus z naught term. So what's a natural generalization I could do?
N poles.
N poles. So then the question becomes, how would you handle n poles? And so, for those of you who like geometry, this is now a nice question. I need to make sure I can choose my contour so that if I have n points, it's okay. So imagine my points as z1, z2, z3, z4. There's lots of ways to do this. So one possible, is I go like this, and then come down here, and I go like this, and I go here, and I go around here, I go here, and I come around here, I come here, I finish this up, I come here like this. And I could do something like this.
Well, I was thinking you would want to have all of them come from the outside.
And that's the other way you can do it. There are two ways you could do it. The other way you could do it is here is z1, here is z4, here is z2, here is z3, poor Umang, this is why you don't go to house. You could come down here, go like this. That one's a little bit bigger, epsilon. And you could do it like that. Does it matter which one of these I use? No. So what you have to do is you have to show me that no matter which set of points I give you, if it's only finitely many points, I can do something like this. I probably don't want my curve intersecting itself. So is there a way to always draw this in such a way? So it's a nice question in geometry topology that yes, you will always be able to do something like this without having things cross if there are only finitely many poles. So what case does this ignore? Countably infinitely many poles. So it turns out our stuff that we've skipped on points of accumulation would actually be very useful here. So we're not going to talk about what happens if the function blows up infinitely often. But you should think something bad must be happening. right? If the function blows up infinitely often, what you can do is divide the circle into 4 pieces. In one of those 4 pieces, it has to blow up infinitely often. Divide one of those into 4 pieces, and you'll get this small, and it's going to be so many blow-ups, something strange will happen. You're not going to have a good function if it has countably many places where it blows up. So fortunately, we don't have to worry too much about those. So the more general version of the formula is now the following. Omega is nice, F is a holomorphic, save poles at Z1 through Zn. And now the only thing that changes is rather than just being the residue at Z0, it's now the sum, and k goes from 1 to n of the residue at Zk of F. So the only thing that changes is now I take the contribution from each residue. Why am I using k for my index of summation?
Because it's this complex.
It's complex analysis, right? I don't want to use I as my index of summation. Okay? Several people have done this. They've used I as their index of summation. Is that wrong?
Yes.
It's technically not wrong. I cannot grade points off of you. I can't even take off points if you use a smiley face as your index of summation. That's acceptable. It's just confusing. Okay? I think I sent you the link to the Onion article about the 27 new trig functions. Did I send you this? All right, I'll send you the article, the Onion. There's a nice article that 27 new trig functions have been discovered. And it turns out there actually are 10 trig functions which you might not have heard of but are occasionally used. Notation matters. Use good notation. It's not wrong to use I as an index, but there's always a danger of confusing things. And so I strongly urge you not to use I in complex analysis. Okay. Any questions on the residue theorem? So let's integrate a function. Can anybody give me a good function that we should try to integrate?
0.
No.
Row 1.
Nope. Yes! Remember to email me. Why did you choose 1 over z squared plus I? Wait, plus I? 1 over z squared plus
1.
plus 1. Why are we doing that?
Because we know the residue.
Yes, we just spent some time earlier today calculating the residues of that function. Right? Foreshadowing. Right? We spent all that time, we can now use that. So, this should be a very natural question as to who would ever want to calculate the integral of 1 over z squared plus 1? I'm sorry? Cauchy. So, you actually don't need complex analysis to do this. Oh, sorry. Force of habit. Minus infinity to infinity of 1 over 1 plus x squared dx. Does anybody remember this integral?
Arctangent?
It's arctangent. So if you remember your trig, it's a lot of fun to remind yourself that the derivative of arctan is 1 over 1 plus x squared. So this is arctan at infinity minus arctan at negative infinity. Arctan at infinity is pi halves, and so if you do the algebra, you get this as pi. If there's time, I will try to show you why the derivative of arctangent is 1 over 1 plus x squared. It's a fun fact to prove. Okay? So in some sense, we don't need complex analysis. But if I instead gave you 1 over 1 plus x to the 4th, what would you do? Do you know a trig function who... So I no longer know a function whose derivative is 1 over 1 plus x to the 4th. I'm choosing this function deliberately because I know what the answer is, and I can check and see at the end of the day, did we do the problem correctly? The other thing is, this is one of the most important probability densities that there are. To make it a probability density, I divide both sides by pi. I have a non-negative function that integrates to 1. That's the definition of a probability density. It assigns probabilities to events. If you've taken a course in probability, hopefully you remember that this is a probability density, and you can talk about things like mean, what's the expected average value, variance, what's the size of the fluctuations. This is a density that does not have a mean, and it does not have a variance. So in terms of trying to test how weak of a condition you need for something, this is a great testing density to use in probability. Alright, we want to calculate this. So there are 2 steps. 1, find a good function of a complex variable. 2, choose contours to exploit, this exploitation is okay, decay. There's technically a third step, evaluate integrals. But the real difficulty is steps 1 and 2. I need to find a function of a complex variable that looks a lot like this function. Any thoughts? Yeah. F of z is 1 over z squared plus 1. When z equals x, that's going to reduce to the function I want to integrate. So this is suggesting a little bit of what the contour should be. So here's my real line. Here's minus infinity all the way down there. Here's plus infinity down here, not to scale. I have to choose a contour to evaluate this integral. Which contour should I choose? I need to get a closed curve.
Half circle. Down.
So do I want the circle going down or the circle going up?
Up.
How many say up? How many say down? How many say up or down? Okay, so we would agree it's either this or this.
What if it's a half donut?
I'm sorry?
What if it's a half donut?
We will find out if it's a half donut. For this problem, I don't expect it to be a half donut. Why do I expect it not to be a half donut?
Those arrows go the other way.
On the bottom one. Third.
This one?
No,
no, the bottom.
Oh, yes. Right, thank you.
When would you expect it to be a half donut?
Well, so a half donut is if something is going on at the origin. Then I might expect a half donut. I might expect some kind of like a detour around that.
Okay, because the
But
problem is
but here the problem is at plus and minus I.
okay.
So the question is, what does this function 1 over z squared plus 1 look like? And so this is the hardest part, is to try to figure out, as z gets large, what does this look like? What would you love to say? I'm sorry? Yeah, I mean, if I have a circle of radius r, I would love to say, on the circle of radius r, this looks essentially like 1 over r squared. And if it looks essentially like 1 over r squared, what's the perimeter of the circle? The perimeter of the circle?
Oh,
Pi r. And so if it looks like 1 over r squared, and the circle has perimeter, pi r, then I'm going to get a decay like 1 over r. So all I need to know is that if this function is decaying like 1 over r squared, I win. This is nice. How's it going to look on the upper circle?
Probably pretty small.
Yeah, it's going to look like 1 over r squared. What's it going to look like on the bottom circle?
R squared.
Yes. This is one of the few problems where it doesn't matter which contour you choose. They both work in this case. Okay? Don't worry, I will make sure that doesn't happen on exams. Okay. So let's consider the absolute value of z equals r. And I want to study the size of 1 over z squared plus r. I'm sorry, z squared plus 1. How big is that? So I care more about an upper bound than a lower bound. Can somebody give me an upper bound for this in absolute value? It's less than or equal to
1 over r.
1.
1 over r. Z squared.
Okay. Not necessarily. If r is very close to 1, then this could be very, very small. Right? The danger is, for instance, if z is close to I, the denominator is close to 0. Now, if r is huge, then yes, the z squared will dwarf the 1. So how large could z squared plus 1 be in absolute value? What's the largest it could be in absolute value? You have triangle inequality. It's at most z squared plus 1, which is r squared plus 1. Right? This is basically saying I have complete alignment Z squared is a real number and positive, 1 is positive, and they perfectly align. I could go the other direction. Z squared plus 1 is greater than or equal to Z squared minus 1. Right? The worst possible case for me would be is if basically Z squared is negative and I have complete cancellation in terms of the orientation. Well, in fact I can even write equal signs here. That's R squared minus 1. So we get that 1 over Z squared plus 1 is at most 1 over R squared minus 1. And it doesn't matter if we go up or if we go down. Okay, so it doesn't matter if we go up or go down, but I still say that there is a natural choice between the two of them as to which one is right.
Top.
Top. Why?
Because the contour that's along the x-axis that we're integrating along, it points in the same direction.
Good. Now, of course, it's not a big deal to do it the other way around here, and then so I'll have to multiply by minus 1, but why multiply by minus 1? This is the orientation I want, let's go with the top. So now, we can finish the problem. And so I'm going to just draw my picture a little bit more. So I'm going to draw the two poles. The two poles are at I and minus I. Here's my contour. Only one of the poles is inside the region. So the fact that the function has a pole at minus I doesn't matter. And so if I call the bottom gamma 1 and the top gamma 2, I have the integral over gamma 1 over 2 pi I 1 over z squared plus 1 dz is just the residue at I of f. Because what's going on at minus I doesn't matter. And what's the residue at I of f? 1 over 2i. Alright, so this is the same as the integral. I'm going to move the 2 pi over to the other side. From minus r to r, 1 over x squared plus 1 dx plus the integral over gamma 2 of 1 over z squared plus 1 dz. If I put the 2 pi over I to the other side, I get just pi. Well, what do we know about this integral as r goes to infinity? Goes to 0. So this is bounded by pi r divided by r squared minus 1, which goes to 0. So I actually had a little bit more decay than I needed. And what does this integral go to? The integral we want. So as r goes to infinity, obtain the integral from minus infinity to infinity of 1 over x squared plus 1 dx is pi. And you don't have to remember your trig, you don't have to remember derivatives of arctangent. Not a bad investment. Now, I mean, I feel like, somebody who's selling Ginsu knives on one of the TV channels, but wait, there's more. Okay? If this is all it could do, this is not so impressive. Because you could have done this already, right? What if I replace the 2 with a 4 or even a 20? I'll replace it with a 4. It's really nice to be at the blackboard. Okay? Do I still have the right decay up top? If I replace this with a 4, this becomes r to the 4th. Okay, my handwriting is so bad, my 2's and 4's are not so bad. Right? So if I replace those with 4's, no problem, I still have the decay I need. What's the only thing that changes? The poles. So where does the function z squared plus 1 have poles?
Z squared plus 1.
Mm-hmm.
Maybe oh, it's z squared plus 1.
Z squared plus 1.
Not 1 over.
So what are the poles? What else? Is there anything else?
Z squared or Z to the
I'm sorry, z to the 4th. Z to the 4th.
Oh, okay.
I to the 1/2 power.
Okay, so now The only thing that changes is, I'll erase this. So now we have to study z to the fourth plus 1 equals 0. So z to the fourth equals minus 1. And so if we write z as e to the I theta, then we need e to the I theta to be negative 1. And so the questions become, what values of theta work? I'm sorry, to the 4 I theta, sorry. Right, when we raise it to the fourth power, we have to get negative 1. So if you think about your circle, this is theta equals 0, pi halves, here's pi, here's 3 pi over 2. So we need 4 I theta to either be pi, or pi plus or minus 2 pi, or pi plus something like that. So what's the first value of theta that works?
Pi over 4.
So theta equals pi over 4. What's the next one that works?
3 pi.
So theta equals 3 pi over 4. And I can write this as pi over 4 plus pi halves. And the reason is when I multiply pi halves by 4, I get 2 pi. What's the next theta I could take? 5 pi over 4, which is pi over 4 plus pi. And the next one, 7 pi over 4, or pi over 4 plus 3 pi over 2. What's the next one?
Pi over 4.
Pi over 4 again, right? I don't distinguish between pi over 4 and pi over 4 plus 2 pi. There's 4 roots. So I think this was like the first homework problem, or one of the first homework problems of this course, was to, how many roots does, e z to the n equals 1 and minus 1 have? So this is going to have 4 roots. So all I have to do over here is just see which roots are up above. So I have 1 over here, this is e to the I pi over 4. I have 1 over here, not to scale, e to the 3 I pi over 4. Then I have 2 roots down there that don't matter. So the calculation proceeds similarly. And then all that changes is what the sum of the residues is. So we'll do it in the residue at z1 plus the residue at z2. And again, this piece will go to 0, this will be what we want. So all we have to do is figure out the residues. Okay, so what is the residue of 1 over z to the 4th plus 1 at z equals e to the I pi over 4? We need to figure this out. So there's a couple of ways to try to do the algebra.
Can we break it up into 1 over z squared plus I and 1 over z squared minus
So
I?
that's one way to do that. So z squared plus I, z squared minus I. It's a great way to factor it. I'll get z to the 4th, they cancel, plus I, perfect. Now when I take z equals I pi over 4, for one of these two factors everything will be fine. But essentially what I can do is I can factor each one of these again. Right? Z squared minus I is z minus I, z plus I. Something doesn't look right here.
No.
No.
Minus v nine plus v nine.
No, because I would need the square root of I.
Yeah.
Right. So what I'm going to do is I'm going to factor it in a better way. Z minus e to the I pi over 4, z minus e to the 3I pi over 4, z minus e to the 5I pi over 4, and z minus e to the 7I pi over 4. Right? I factored my number. And from what we talked about before, notice the z minus the root occurs only to the first power in the denominator. So all I have to do is then evaluate this at I pi over 4. And then all I have to do is evaluate this at 3 I pi over 4. And then just do the algebra. So now, evaluate to get residue. So for example, the residue at e to the I pi over 4 of my function f is just 1 over e to the I pi over 4 minus e to the 3 I pi over 4, e to the I pi over 4 minus e to the 5 I pi over 4, one more, e to the I pi over 4 minus e to the I 7 pi over 4. And that's one of my residues. And then I do it again for the other one. I don't see as many smiles as when we had x squared. Okay? How many people think that this is fun to evaluate? It's okay to admit it. Go first. Alright. So nobody seems to be jumping for joy at evaluating this. How many people could evaluate this if their life or something even more important, their grade, depended on it? Yeah, I mean, basically e to the I pi over 4, that's, cosine pi over 4 plus I sine pi over 4. This is root 2 over 2 plus root 2 over 2i. And then the next one would be negative root 2 over 2 plus root 2 over 2i. It's not going to be fun, but you could evaluate this. Okay? So with a little bit of work, you can finish the problem. The interesting thing is the sum of the residues, when we multiply by 2 pi I, has to be what kind of number? Has to be a real number. Why?
It's integrating real numbers.
Yeah, we're integrating, it's supposed to equal this integral, which is real. So at the end of the day, everything is going to miraculously cancel. So to some extent, depending on how you're doing the algebra, you can even drop a little bit of things, because you never have to worry about imaginary terms. Now for this one, it's not going to help you. It's also a good idea not to drop imaginary terms, because if you make an error, this is a good way to detect it.
Also,
Yes.
can't that have an I in it, which will be cancelled by the 1 over 2?
No, I said when you multiply by 2 pi, exactly right, that you have to be careful. My wife is the new director of graduate studies in the marketing department at UMass, and so she had all the doctoral students and some of their significant others over. And so I was taking orders for the grill, how many people wanted hamburgers, how many people wanted cheeseburgers, and then there were 3 different types of cheese that my wife wanted to serve. Oh, I think I might have gone on the camera. And after getting how many people wanted the first 2 types of cheese, did I need to ask how many wanted the 3rd type of cheese? Yes, these are marketing students, they can't add. It actually didn't add up right. So it was really good that I did a redundant check. It turns out one of the people wanted a veggie cheeseburger and counted that as both a veggie burger and a cheeseburger. It was a counting issue. So this is, okay, so you may not be in the position where you are married to a professor of marketing who's in charge of bringing graduate students to your house for a barbecue, but you could be in a similar situation. Can you calculate something multiple ways? If so, it's a good check. You could easily ignore a lot of the calculations here by saying, look, all that matters is the real part. It's good to still do the entire thing, because if you make a mistake, you can hopefully detect that. What do you think the final answer should involve? Pi. If you look at everything down here, it's going to be involving things like square roots of 2. There's no pi's at all in this. Where's the pi going to come from? Yeah. So in fact, it's going to be pi times some nice function of square root of 2. So you have a nice shape for the answer. So again, I hope this gives you some sense of the power of complex analysis. That we can handle an integral like this without too much trouble. So I'm going to give you, in addition to the homework that you have for tomorrow, I want you to think about a function or 2 functions for Friday. I want to understand the integral from minus infinity to infinity of sine of x over x to the m dx. And m will be either 1 or 2. So I want you to think a little bit. Do these integrals exist? If so, do they exist for both values of m? If so, can I evaluate this using tools from real analysis? If not, if I want to do this with complex analysis, what would my function be and what would my contour be? So again, I'm not asking you to write this up, I'm not asking you to hand this in, but I want you to just think about this a little bit before class on Friday. Okay? What would you try to do for the function? What would you try to do for the contour? Remember, you need to exploit decay. And a fact which might be useful is, sine of z is e to the iz minus e to the minus iz over 2I. Cosine z is e to the iz plus e to the minus iz over 2. So those might be useful. Okay, so think about this. Okay.